All right, let's continue graphing. Let's try, the next few are going to be a little more complicated. And just to give you an idea of some of the things we're going to have to start to notice about functions, we're going to have to analyze them and think about them a little more critically than we used to before. Because as you would expect, the functions are going to just get more and more complicated in calculus. Okay, so here's one. 1 over the square root of 9 minus x squared. The last one on the previous video was just the square root of 9 minus x squared. We saw that was the top half of a circle, but this is 1 over that. So let's start with the domain and the range. These are tools that kind of help you graph. Think about what the graph of the function would look like. Now for the domain, okay, we've got stuff under the square root, which we know has to be greater than or equal to 0. But because it's also in the denominator, right, we don't want the denominator to be 0, I should say. So in this case, we would want 9 minus x squared to be just greater than 0, not greater than or equal to. You can do a number line technique like we did on the last video, or if you just think about it, what numbers would make this true? They would have to be numbers between -3 and +3, not including. Again, if x was 3, the denominator would be 0, and I would be dividing by 0, which is not allowed. So that's why we're taking off. The parentheses means not including, either 3 or -3. Okay, so drawing from your knowledge from pre-calc, what if x was 3 or -3? It's going to be undefined, and we got used to associating that with a vertical asymptote, and that's exactly what's happening here. This graph will have a vertical asymptote at negative and +3. Now, the range of this function, sometimes the range isn't so easy to see. So a lot of times what we'll do is we'll just analyze it. We'll just think about it. It's not always going to work this way, but in some functions, you can still get a pretty good idea of what the range is by just thinking about what's the smallest output I could ever get out of this function. To answer that, what I would probably use is another question. Fractions are small when denominators are big. So to figure out what the smallest output is, what I want to think about is what's the biggest thing this could be, the denominator. And can you see that if x was 0, you're going to get the square root of 9. That's as big as it's ever going to be, because anything other than 0, you're going to be subtracting from 9. You're going to be making that smaller. So the smallest output of this fraction is going to happen when x is 0. I'm going to get 1 over the square root of 9, which is 1/3. Conversely, fractions are big when the denominator is small, right? My numerator can't be changed. The only thing that can change is my denominator. So to figure out my largest output, I want to think about what's the smallest I can make this denominator. And that's going to be when x is pretty close to 3, right? The closer I get to 3, the smaller this gets, and that makes the stuff under the square root get really close to 0. Taking the square root of a small number makes it even smaller. So and this is something we're going to be focusing a lot on this quarter, when you get a fraction that you realize the numerator is a number and your denominator is really small, that's going to generate a big number, okay? Taken to the extreme, if this gets infinitely close to 0, this fraction, this 1 over a small number, could get infinitely big. So my range for this function would go from 1/3 to infinity. Another thing that would be useful is maybe deciding if this is even or odd. And remember how you can do that is if you plug in a negative x value that's in your domain, how would that compare to the positive counterpart of that number? In other words, what would you get if x was -1 or if x was +1? Do you see, because we're squaring it, you would get the same thing? And that tells you this is an even function. So the graph of that function, now I plotted this here. And there's my check that it's an even function. So we have our two vertical asymptotes. Our smallest value happened when x was 0. That's 1/3. That's your y-intercept. And we saw that as x gets closer to 3, as we get closer to this vertical asymptote, my y value is going to get infinitely big. So you can imagine this function approaching that vertical asymptote towards infinity. And because it's an even function, the nice thing about that is once you know the right side, the left side is going to do the same thing, right? It's going to also approach infinity. All right, let's try another one. I'm going to cover up the graph here. There we go. Okay. So it's a very similar function to the last one, but now I have x over the square root of 9 minus x squared. So let's run through some of the analysis here. The domain, if you'll notice, the domain is still controlled by the square root, and since it's in the denominator, it's the same as number 3. My domain is the same. This whole function lives within x being between -3 and +3. And just like number 3, because my function would be a number over 0 when x is plus or minus 3, I'm going to have a vertical asymptote at x equals plus or minus 3. Now, the range for this one is not so easy to see. And the reason why, compared to the previous problem, is not only would my denominator change depending on what I plug in for x, but also my numerator. Okay, so at this point in 21a, no one's going to ask you the range of a function like this one without some use of a graphing calculator, perhaps. There are certain functions like the one I just did where I think it's fair to ask for the range. I think it's possible to think about the outputs and conclude what the range is. But this one would not be one of those. So let's just skip that. Okay, let's not worry about that here. To check if this is an odd or an even function, we're going to plug in -x and see what we get. So I put a -x in there. I put a -x in there. Of course, squaring the -x is going to keep it the same. And if I just take the negative I had with the x and put it in front, I can see that this is just going to give me the negative of f of x. F of -x equals negative f of x tells me this is an odd function, so it's going to have symmetry about the origin. I'll tell you what, if for practice, maybe pause the video and see if you can use this information to try to graph the function. See if you can figure out what it looks like. Go ahead and pause the video, and then I'll show you. Okay, hopefully you've done that and come back, and here's what the graph looks like. Now, one thing that might have been a little bit tricky was seeing what happens. We knew there was going to be vertical asymptotes, and we knew it was an odd function. So one thing you would want to decide on is what happens as you get close to that vertical asymptote. We know whenever we get close to a vertical asymptote, the graph's either going to approach it going up to infinity or possibly down to -infinity. So if you just imagined a number close to 3, close to +3, what would happen if you plug that into your function? You would get 3 over a really tiny number. And what we discussed on the previous problem, when you get a number over a small number, that's going to get really big. So that would approach infinity. So that would show you that this half is going to go this way. Because it's an odd function, remember the symmetry about the origin, you could reflect the right half this way and then this way to get the left half. Okay, let's continue. Let's take a look at this one. I'm not going to show us the graph yet. X to the 4th times the square root of 9 minus x squared. Okay, I've got all my analysis here, my domain. Once again, 9 minus x squared, this time greater than or equal to 0. It's not in the denominator, so it could equal 0. And that's going to give me negative 3 to 3, including. So I have brackets on there, including the endpoints. Another one where the range is not something for this particular function, that's not something that anybody would expect you to know right now. So let's skip that one. We can't tell that yet. I found, okay, just to get some extra points, I did find some X-intercepts. If you set X equal to 0, you're going to get 0 and plus or minus 3. And if you test for even or odd, if you plug in negative X for here and for the X squared term, notice because you're raising negative X to an even power, they're just going to go right back to being the same function, right? You're going to get the same function. So this is an even function. Okay, so if you want, pause the video, see if you can get the graph, and I will show you in a couple of seconds. And this is what you should have, something like that. The part that we won't know is we won't know how, what does this part look like? Does it have more wiggles or whatever? We don't know, but we did know it had X-intercepts at 0 and 3, and it was an even function. And perhaps if you plugged in some numbers between 1 and 3, you could probably generate some points here to get some values. So you would have a little more specific values to look at. It should look something like that. Okay. Let's try one with a sign in it, because we do know, okay, I started off here with the testing if it's even or odd by plugging in negative X into both X and the sign of negative X. Remember that sign is an odd function. And because it's an odd function, the sign of negative X is equal to the negative sign of positive X. Remember, this is because sign is an odd function, because sign of X is odd. That's why we can do that. These two negatives then would make it positive. So we end up with the same function, which means this is an even function. So it's going to be symmetrical about the y-axis. I didn't do the domain, but let's just talk about it. This domain for this function, you can plug in anything you want for x here, and we know the sine function, you can take the sine of anything. So the domain of this function is negative infinity to positive infinity. We don't have any restrictions on what we can plug in. Okay, to get some extra points on the graph, we could find some x-intercepts, and we're going to get x-intercepts at 0 for this one, and everywhere sine of x is equal to 0, which would be, okay, there's an infinite number of places. Negative 2 pi, positive negative pi, 0, pi, 2 pi. There's an infinite number of places where sine is equal to 0. Now, additionally, what you might want to consider is what happens if you start plugging in x values, bigger and bigger x values, right? When you go from 0, pi, 2 pi. The sine function we know will always be between 1 and negative 1, but this is going to make it bigger and bigger and bigger. So what that graph is going to look like is something like this. Okay. Notice it's crossing the x-axis at all of these values, pi, 2 pi, 3 pi, but and it's going to oscillate because it has a sine in it. It is going to have that sine wave, but the amplitude of these oscillations is going to get bigger and bigger and bigger because of this term, because as x gets bigger, that's going to become a bigger number, right? And the left half, we showed that it was even, so if you figure out what the right half looks like, the left half is just the mirror image of that. Now, another way to see why the oscillations get bigger and to think about the range of this function. One way we can do that, this is something we're going to look at in the near future. If we start with the sine function, and we know that the sine of anything is always between -1 and 1, the sine of any angle. If that's true, and I multiply this inequality by x, everybody by x, then x times the sine of x will always be between -x and x. And notice that was the function we were just graphing, right? What this tells us is the graph of x, sine of x, the graph of our function will always fall between these two lines, the line y equals x and the line y equals -x. So this graph that I had graphed on the previous page, the magnitude of these oscillations, what's going to happen is going to keep running in. It's going to go up until it hits y equals x, and then it's going to come down until it hits y equals -x. It's going to keep oscillating between those two lines, which will hopefully convince you that those oscillations will get infinitely big. So our range is going to be from -infinity to +infinity. Okay, so now that idea, let's just show you this last example here. What if I made it x squared times sine of x? Well, for one thing, okay, going off what we were just talking about, using the idea that sines between -1 and 1, this time multiplying everybody through by x squared, that shows me that my function, this particular function, will always lie between -x squared and +x squared, which are two parabolas. Okay, so I've got sketched here y equals x squared, y equals -x squared, and you can see my oscillations are always bouncing back and forth between those two graphs. This one happens to be an odd function. If you plug in -x and square it, you'll get the same thing, and the sine of -x is the same as the negative sine of +x. So I can take that negative and put it outside. So it's an odd function. So what actually happens close to the origin is the left half is just the opposite of the right half. And so this one goes up. That's why this one goes down over here. But hopefully you can kind of see how these ideas of knowing the domain, the range, whether it's even and odd, in some cases, trapping your function between two other functions, these are all tools that we're going to use going forward to think about the graphs of functions. Okay.